Welcome everyone, and thank you for attending today's webcast, Getting Started with Nastran In-CAD Training 2-Hour Quick Start. Our presenter today is Robert Smith. He's a solutions engineer with Hagerman & Company. Before we get started, I'll let you know that you're in listening only mode. If you have questions during the presentation, you can type those into the question panel located on the right-hand side of your screen, and they will be addressed via email after the presentation. As we close down the session today, you'll be prompted to fill out a survey. We ask that you take a few moments to fill that out. Additionally, all registrants will receive a follow-up email tomorrow containing a link for the recording of this presentation. And I'm going to hand things over to Robert now.
Okay, thank you very much, Ashley, and yes, hello everybody. So, my agenda today is ambitious. My goal today is to get you up and running on your first static stress, thermal, or thermal stress analysis. This should feel a lot like taking one of our full classes remotely, except I'll probably be in a hurry to say everything I want to say in under 2 hours. We have a lot of people in attendance today. We try to limit our classes, though, to 8 or 10 people, and often it's less than that. So in a real class, this would be a two-way street, like a conversation. You'd be able to interrupt me and tell me to slow down, ask me to go over something in a little more detail, or ask follow-up questions, and that just won't work today. In fact, while I have provided you with the models that I'll be using, I actually encourage you not to try too hard anyway, to follow along. If you do fall behind, don't worry about it. I'd rather you be able to pay attention to what I'm saying, and we'll provide you with a recording of this event, as Ashley said. So you can set up the models later at your own pace. If you don't have the software today, no problem. There is a 30-day trial available. So go download that later on and try out these models. If you have any questions, again, as Ashley already mentioned, drop them into the chat. And if we don't get back to you during the session, and we probably won't, we'll definitely follow up with the email later on. So we'll be focusing on linear static stress analysis type today. We'll also be getting into steady state heat transfer analysis and how the two tie together into a thermal stress problem. The full class will touch on other analysis types, but the focus is still on linear static stress, and that's because it's the most common type of analysis that's run. And it's not quite as easy as you think, and the concepts involved in that typically don't apply to any subsequent analysis type that you'll use. So, a quick review of the fundamentals. What is stress analysis? Let's take, for example, this cantilever beam. And let's say I want to know how much this beam is going to bend downward due to the weight on the beam. FEA says a day, right? Yeah, except problems like this are pretty easily solved by hand calculations too. In the real world, our structural problems tend to be a bit more complex than a cantilever beam. So show me a hand calc that's going to predict this event, right? Now, to be fair, this problem would be found on the extreme end of the FEA complexity scale, with my little cantilever beam problem sitting on the other extreme. Most of your problems will fall somewhere in between the two. So, how does stress analysis, or FEA to use another term for it, how does it actually work? Let's start by breaking this up into 5 simple categories. Start with the input. We take some defined geometry, which is your CAD model. We define what the geometry is made of, and we identify areas where the geometry is loaded and constrained. We feed all this into a solver, which in turn spits out results. You may have heard terms like pre-processing, which means all the stuff at the front end, the setup, or post-processing, which is the part where we process the results and dig out the useful information. In the early days of FEA, these tasks, pre-processing, solving, post-processing, they were all handled by different software products. Some products still operate this way today, but it's becoming more common to see all these functions rolled into a single interface, as is the case with Nastran In-CAD. In fact, in the case of CAD-embedded systems like the Nastran In-CAD, the idea is to iterate. The fact that the FEA model is so closely tied to the design model will hopefully allow you to rapidly iterate on the design. And this tool is what we call an upfront analysis tool for that reason. It's not intended for validation at the end of the design, though that doesn't mean it can't serve that role. It's really meant to be part of the design process from start to finish. Another tool in your toolbox, really, to help you make informed decisions about the geometry and the material selections. So let's take a look at that geometry piece. This is an element, the building block of the FEA model. This is a type called a line, and is meant to be a simpler way to represent real-world 3D objects like this bar. These line type elements are available in Nastran In-CAD, by the way. We take a deeper dive on those types of models in the full class. More commonly, you'll be using 3D geometry. 3D geometry uses elements as well, it's just a different type. In this case, tetrahedral solid elements are used. The other important piece of FEA geometry is the node. And this is where the elements connect to one another and where forces and constraints are applied. They're also the points where we get results back from the solver. I'm only showing you this line element because it's about as simple as FEA gets, and I kind of want to show you some of what's happening in the solver in the background using a very simpler model. So next, the material box. In the case of a cantilever beam problem like mine here, using line elements, all I need to know about the material is the elastic modulus. That's it, just the one input. So what is it? This is a stress strain curve. If I have performed a whole bunch of tests where I pulled on a piece of steel with a known force and measured how much it stretched, and then plotted that information on a line graph, it would look something like this curve. Ductile metals, like steel and aluminum in particular, display a nice straight line at the front end, or straight enough that we can assume it's straight. This region is known as the elastic region. It is so named because if I relieve the load at any point in this region, the material will snap back to its original shape. No permanent deformation, no damage. This is the only type of material behavior that linear static stress analysis can simulate. So I'll get back to that later. The slope of this straight line, or its vertical distance divided by its horizontal distance, stress over strain, is the elastic modulus. It comes out to be a number in the same units as pressure, like PSI or Pascal. It's the stiffness of the material. And that's all we need for our beam analysis. If you're working in 3D, and you probably are, you'll also need Poisson's ratio. This just describes, for instance, how much my material sample shrinks laterally as I stretch it axially. These two properties then, elastic modulus and Poisson's ratio, are the only required properties to solve basic stress analysis in 3D. You may need density if you want to consider body loads like gravity. So the material library contained in Nastran In-CAD already contains this basic information. Next, the loads and constraints. Let's say my cantilever beam is actually the boom of this jib crane. When I start to set up the analysis, my first step is to determine the scope of the analysis, or where its boundaries are. If all I want to know is how much my boom is going to bend when I load the hoist, I don't need to model the whole crane. My beam element will represent the portion of the boom that I care about, between the main support and the hoist position. Loads and constraints often replace parts of the model that I'm not concerned with. For instance, I'll ignore the main support and replace it with a fixed constraint at the left end of my beam. This just means that the left end is not allowed to move. I placed it on the boundary of my analysis, which is why you'll hear them referred to as boundary conditions sometimes. I'll replace the hoist with a force that represents the load applied by the hoist onto my boom. Notice that it's also on the boundary. The resulting FEA model will look something like this, and that's the idea. So we have all the pieces. We have the geometry, materials, the loads and constraints. When we hit the button to run the analysis, we send the information to the solver. So what happens then? Well, it's not as magical as you might think, at least not when we're talking about linear static stress. F equals KD. This is the heart of FEA. F is our forces. K is the stiffness of the model. You can think of this as your geometry, materials, and constraints. All these things contribute to the picture of the structure's overall stiffness. And then there's D, which is our results. Actually, it's the displacements, or in other words, how much did the structure move? That is typically our output, though, and from that we can derive lots of other fun things like stress and strain. In fact, the equation is more commonly arranged in this way. We feed the solver our forces and the stiffness, and it spits out the displacements. And that's it, folks. The fundamentals really are that simple. It gets a little more complex with 3D elements, but the basics are the same. All right, so the model we'll be using today is a CPU water block. Now, I'm betting I'm not the only nerd in this class, but if you know what a CPU water block is for, then you're my kind of nerd. These things are part of a water cooling loop used in high-end computers. The CPU water block is strapped to the CPU in place of passive or air-cooled heatsink that it comes with, typically so you can overclock it and get a little more performance out of your processor. This is a consumer-grade cooler meant for gamers or other computing enthusiasts. I got the model and most of these renders from GrabCAD. So I'll give a shout out to E. Washbrook. Nice model, man. CPU water blocks are often made of a copper base that contacts the CPU itself. Usually there's some kind of mounting bracket which maintains the pressure between the base and the CPU. The force is applied via screws, thumb screws in this case, that screw into standoffs mounted in the motherboard. There are springs between the thumb screws and the mounting bracket, so the force is applied evenly and you're less likely to damage anything by over-tightening. We're going to study the stresses that are developed in the assembly when it's tightened against the CPU, including the effect that thermal expansion may have when the system heats up. Chilled water is forced over the copper block through some tortuous path, rapidly removing heat. In this case, an acrylic block contains the flow and directs it through some fins integrated into the block. Nastran In-CAD does not simulate fluid flow. Most FEA codes are either structural or CFD, not both. Autodesk does produce a great CFD tool, which is how I got the image you see on the right. In structural FEA, we typically apply coefficients to the surfaces, which contact fluids in real life, in order to approximate their heat transfer effects. And that's what we're going to do today. If you are an Autodesk CFD user, we can import temperature and pressure data from CFD. You'll see how, because it's the same method we use to transfer thermal loads from one Nastran analysis to another. All right, we'll get back to this. This is actually the setup information I'm going to need in a bit. So I'm going to jump into the software itself now. So I am trying to keep this to the 2-hour mark. If I do approach that time limit and think I'm going to go over it, what I'll do is I'll give you my closing remarks, then come back. And if you're interested, stick around and I'll finish the model up. But I may be rushing. We actually have had some audience participation in some of these where I'm in such a hurry to get this stuff done while I'm babbling all the way. I miss a few picks and clicks and find myself troubleshooting on the fly when I don't get any results. So keep a sharp eye on it. Maybe you can help me out if you see I missed something. You can bail me out in the comments there. So this is the 3D model itself that I got from GrabCAD. You can see it's a fully detailed 3D model assembly in Inventor. The files I gave you, by the way, are Inventor 2018. So if you are running anything earlier, I can send you a step file. Just let me know in the comments. I'll email you a link to that, so you'll be able to do this later on in Inventor 2017, for example. These are 2018 files, and you should have gotten two things from me. One is this fully detailed model, which is an example of what a real design might look like, something that you need for manufacturing and documentation purposes in Inventor, with all the nooks and crannies that come with it. And then you'll have a version that I've stripped down for simulation purposes, which is what I'm actually going to use for the model today. This kind of thing isn't uncommon and usually a critical phase in the simulation process, determining what's important for your model. Little details on my thumb screw, for example, those little grooves. I'm not going to spend the computational overhead to try and include those in my analysis when they add no structural value and have no effect on what I actually do care about. So I would remove them. And in fact, in this particular model, I removed the screws altogether. And those are going to be replaced by a force. The springs themselves are actually pretty complex FEA problems if you've ever tried to design a spring, and people do. That would be a case where you'd want to mesh a spring in 3D and actually analyze it. But if it's just part of a larger system meant to impart some stiffness in the model, well, you're not going to include that. You're going to exclude that and replace it with an element that kind of approximates a spring. And you'll see me do that too. Lots of little fillets and chamfers. decorative features like the company logo cut in the side, a little decorative badge on the top, little grooves that are just for looks. Get rid of that stuff. You know, it's just going to cost you unnecessarily. And that's what you'll see in the strip down model that's been provided. Unnecessary parts, unnecessary features are removed, and in some cases, features added. And you'll see why as I go to set things up. Things like these work points that I have and extra faces that I've put onto some of these parts are strictly there for simulation purposes, and you'll see why. And you don't necessarily have to know that you need those things ahead of time. And that's one of the benefits of working right inside of Inventor. If I'm humming along in Nastran In-CAD and realize that I need to split out a face or add a work point so I can pick something, I just get back to the modeling environment, do what I need to do, and then jump back into the In-CAD environment. It's pretty straightforward. So let's do that now. Let's jump into the In-CAD environment and get started. See how I'm looking for time. I think I'm on track. What I actually want to do is not jump right into the assembly right away. I'm actually going to just start with a single part analysis. And this isn't uncommon either. One of the primary things I'd advise you to do is start simple and work your way up in complexity as you have success with the simple stuff. So even if I'm experienced in a certain product, and I would still probably start off looking at the single part that I care about in its own analysis before I start incorporating other pieces, just to get myself a quick feel for how it's going to perform before I spend too much time on it. So I'm going to open up just that mounting bracket, that stainless steel mounting bracket in its own window here, and we'll just analyze this single part first. So you're going to get to the In-CAD environment by going to your Environments tab in Inventor. You should see a button there called Autodesk Nastran In-CAD. It is a separate install if you recently got this software as part of the new product design and manufacturing collection. It does not automatically get installed with Inventor necessarily. It is installed separately. It just runs inside Inventor. But once you've done that, you should see this button there. And all it's going to do is it's going to keep you inside Inventor, but bring up a new environment, basically a new tab with some new palettes of tools for you to use for analysis. All right. So here we go. You can see I've got my new tab. All right, and this is kind of like a workflow that they've put on this ribbon here. You sort of work your way from left to right, starting by building an analysis, setting it up with idealizations and materials, loads and constraints, editing the mesh, and then running and interrogating results. So it kind of flows just like it's laid out there. Now, Nastran In-CAD does some things automatically the first time you launch, and it has done that here for me. It's basically created, let's see, do I have my free drawing tool here? If you look in this portion of my interface here in the browser, it's actually created our first analysis, analysis 1. It's made it the linear static stress analysis type, simply because it's probably what you're going for. It's the most common analysis type used. Even if you plan to go on to something more advanced to make a nonlinear problem, it's usually a good idea to set up a static problem first and get a feel for the problem. So it picks that for us. We can switch it at any time. It's also created our first idealization. So what is that? This solid 1 is the idealization it's created. So I'm just going to double click on that to bring up the settings for solid 1. Okay, so idealizations are basically how we tell Nastran In-CAD what type of element we want to use to mesh. We have solid tetrahedra elements. We also have the line-based elements I discussed earlier. And there's another element type, a shell, which is really geared towards thin bodies like sheet metal parts. So you'd see those options in this drop down here. It's assuming I want solid elements correctly in this case. I'm using a 3D model that is relatively chunky. It's not it's thin, but it's got a lot of features cut out of it, so it's not really a big flat plate that would be appropriate for shell, and it's certainly not a line element problem. That's really good for structural members, frames, things of that nature. So you're telling it what type of element you want to use, and you're also telling it what material you want to use. That's basically what an idealization does. How do I want to mesh it? What material properties are going to get assigned to that mesh? So it's detected the solid, it's assigned it a solid idealization. It also picked up the material that existed in the CAD model. So I had assigned stainless steel to the CAD model. It's detected that, it's assigned it for me, and correctly in this case. If I want to explore other materials, I'm absolutely free to do that, but this much is already set up for me, ready to go. So that kind of, if you're looking at this ribbon as a workflow palette, it takes us about this far, right? We've got a new analysis already. We're not importing it from inventor stress analysis. It's assigned an idealization for us, which includes the material that was already in there. So now I'm kind of working from this way on. I'm not going to do any connectors yet. You'll see that further along in the model. I'm not going to use any of these tools, which are based on the thin bodies, the shell element meshing. So, and structural members is for line element meshing, all stuff that we get into in the full class, but not here today. So really, I'm at the point where I'm ready to start assigning constraints and loads to this. So my constraint, when I bring up this dialog, the default is basically a fixed condition. Whatever I click on now in the model is going to be held down no matter what loads I apply. I'm basically saying, for example, this face, the face that's coming into contact with my copper base part in the full assembly, is not allowed to move. So I don't have to touch anything in here. It's already set for a fixed condition. I might want to give it a new name. All these loads and constraints, all these dialogues that I'll be bringing up, I can give logical names that'll make it easier for me to see what they are when I look at them in the model tree at a glance later on. So that's fixed. My loads are going to be 12 pounds on each one of those thumb screws, kind of the maximum we intend to design for. So I want to see what kind of stresses develop in this plate under that kind of loading, and eventually the entire assembly under that loading. So the screws are no longer here. I'm basically going to be putting the force that the screw and the spring are imparting onto my mounting plate. I'm going to be putting it on the location where the spring makes contact with this plate. And that is why I broke out those little circles as a separate face. So let me show you. I'll bring up loads. It's already set to force. There's lots of different kinds of loads we can use, but I'm going to go with the force. It's pretty commonly used. All right, and now I'm picking locations where that force is going to get applied. And those 4 pads is what I'm going for. So that little circle, sorry, didn't mean to make anybody sick there. That little circle there was not part of the original CAD design model. It was just a single face on top here. But by using Inventor's split command, I was able to isolate just that circular area, which now allows me to select just that area for my load. Otherwise, I would only have the entire top face of the plate to pick. So it's a pretty common technique to have to use that split command. You just sketch a circle, and it splits out that face. So you have a nice discrete area to pick. So on these 4 pads, I'm going to be putting 12 pounds of force in the negative Y direction. The triad you see here given for our convenience is based on the coordinate system that's currently in use for this command, and that coordinate system comes right from the part that I'm in. Once we get into the assembly, if you're familiar with 3D modeling, you know the assembly will have its own coordinate system, the parts will have their own coordinate system. We can pick which one we want to use, but it'll always show you in the load command which direction is which, just temporarily for convenience. So I know I kind of want to push downward, right? So I'm looking at the Y direction, and the arrow on that triad is pointing up. I want to go opposite that, so the load magnitude itself will be a negative value. These 3 boxes here correspond to the X, Y, and Z directions. That's just one of the ways that we can specify the direction of our force. We could also say just make it normal to the surfaces that I picked, or allow me to pick another geometric entity, say an edge or a face or even a sketch in the part that, say I was looking for a load off at some weird angle. The easiest way for me to point the force in that direction is to give myself a sketch or a work axis that's already assigned at that weird angle, and then I can pick it in this command and my force knows which way to go. But the default is this components, and I'm putting all of my force in the Y direction, so everything goes in that Y box. Nastran In-CAD will start to build up these little symbols, these little glyphs in the model, visual indicators of what you've applied. There's our fixed condition over there. I can click on that, see where it's assigned. The force magnitude glyphs will show me what direction they're going, and they are scaled by their magnitude. So that comes in handy to know if I forgot to put the negative sign in, I'd see the arrows going up, and visually that would be a quick way for me to see I had missed that negative sign. So this model is ready to run. It knows what? It knows its geometry, which is the CAD model. Really, it's the mesh that's going to get built from the CAD model, but we'll get there. It knows what it's made of. That's part of the idealization as well. And we have loads and constraints. We have a problem to solve. So at this point, we're ready to go to run. Yes, there are settings to control the mesh, and we're going to get there. We'll come back to those settings in a bit. I just want to get some quick results. So I'm going to hit that run command. It's going to send this information to the Nastran solver. It's going to spit back results when it's done. This one runs pretty quick. And load those results for me. This is a pretty common example of what you're going to see in structural FEA. We have what's called the contour, which is the colors that are painted onto the model. Those colors correspond to a certain quantity, in this case, solid von Mises stress. So the actual magnitude of the stress can be looked up on the legend to the left. The colors correspond to an actual magnitude there. It's always going to scale from blue to red. So the highest will always be red. It doesn't mean it's bad. It doesn't mean it's failing. It just means it's the highest. So we can quickly look at the model, see where the areas of highest stress are, where the lowest are. So I can, just by looking at the top of my legend, know that the highest stress that's going to be found on this model is about 20,000 psi. If I remember right, the yield stress for this material is about 23,000 maybe. So we're under that. We're looking good. It's also severely deformed, right? It looks worse than it is. Also very common in static stress is to exaggerate the deformation, because typically in static stress you're working with displacements that are small. In a part like this, which is about 4 inches across, you'd be expecting results in the thousandths of an inch. You know, you start getting up over that into like tenths of an inch, you might be exceeding the kind of displacements you'd be comfortable with in a static problem of this scale. You might be going into nonlinear territory simply because the directions of the force might be changing. You might be exceeding the yield stress of the material, stuff like that. So because displacements are typically small, they exaggerate them so that you can see what direction things are going, which areas are deforming the most compared to others. It's just a visual aid. And we can animate this deformation as well to give us an indication of what's happening to the part. In-CAD gave us 4 plots. We were just looking at the one that it brought up automatically for me, which was the von Mises stress plot. Von Mises stress is most often compared to your yield criteria or ultimate strength if it's a brittle material. If von Mises is higher than your yield, you're yielding. If it's lower, you're not. Obviously, there's a bit more to it than that, but in general, that's how it's used and how you can use it quickly. But there's 3 other plots that it's given us here. Displacement, for example, throws up the deformation, throws on a contour, but the contour means something else. It means the actual displacement, in this case in inches, seen on the part. So I can see my maximum displacement is actually about 5/1000ths of an inch. So trying to see that in an animation or a still screenshot would be difficult, and hence the severe exaggeration they place on the model. There's another useful plot there called safety factor. Safety factor looks at the yield criteria, which is stored inside of the material properties, and compares the highest stress value, or really the local stress value, to that criteria, and tells you how far away you are from failure, essentially. So my minimum safety factor, I can see with this little flag In-CAD has given me, is about 2. And theoretically, that means I could double the load that I put on this thing, and I would just then be approaching the yield stress of the material. It's not really a linear relationship like that necessarily, but in general, that's what it means. I have a safety factor of 2 minimum. And then there's one that's just deformed. No contour, just the deformation. Now you have full control over these results, creating a plot of your own with all kinds of options that we would go more in depth in a full class. that's really all I wanted to show you with this quick analysis, this first single part. At this point, we can finish the Nastran In-CAD environment, close this file, and go back to our full assembly. All right, looking pretty good for time. We'll see how that goes. Back to our full assembly. I'm going to do the same thing now. I'm going to launch it into the Nastran In-CAD environment. And what this is going to create is the assembly's own analysis environment. It's separate from the one that's contained inside of that single part. Each part, each assembly gets its own Nastran model associated with it. So I get a fresh start when I launch this one in. And it's going to do the same thing. It's going to create for me my first analysis of linear static. It's also going to create idealizations for each one of the parts I have because they're all made of different materials. So that's a good 2 or 3 steps or more done for me already. It's detected the materials I had assigned in CAD, assigned those into the idealizations for me. So again, I'm a good deal along the way towards getting some results already. Now I'm still going to keep it simple and build complexity as I go. So before I get too fancy, let's just add a constraint, leaving it fixed. I'm not going to play with anything in there just yet. What you can see in my model here is I do actually have a little block underneath there that represents the CPU. And that just gives me something to push against. You know, when I put pressure on the mounting plate, I want to actually be pushing against a part that's about the same shape as my CPU. So modeling it in there gives me that. So now that fixed boundary condition that was once on the face of my mounting plate is now moved, and it's going to be on the bottom of the CPU, because really the boundary of my analysis has moved, right? By adding parts into the problem, I've kind of pushed out the boundaries. I'm including more parts in the problem now. So my boundary condition has moved. You don't put boundary conditions in between parts. It's really meant to be on the edges of your simulation. So I'm going to fix it there. I'm going to apply that same loading to those 4 pads on my mounting plate. Negative 12 pounds on each in the negative Y direction. But I'll give it a useful name. I'll say it's negative 12 pounds in the Y direction. That means I can look at it. Once I hit OK here and create it, that load now exists in my model tree, and I can just look at it and tell what it is without seeing load 1 there, load 2 there. And that's going to come in handy later when I start to build up different combinations of loads in subcases. But I'm going to keep it simple for now. I'm not going to add any more complexity at this point. I'm just going to give it a run and see what I get. Okay, and what I get is failure. Now hopefully this doesn't happen accidentally during our presentation today. This one was intentional. Now as soon as I hit OK, that log that was scrolling on the left-hand side as we were running in the solver, it didn't disappear, but it switched me back to my model tree. If I want to see that log again, I'll go up into the top of my browser and select that tab. This is what was scrolling as we were running, and it's just kind of feedback logs coming from the solver. And down at the bottom there, I can see a fatal error, stiffness matrix singular. They actually seem to have changed the terminology with the latest release. If you're looking at 2017 or even an earlier version of 2018, it might say singularity detected. I can see why they might have changed that, because the singularity can mean something else. But what this is it Nastran's way of telling us that we are under constrained. We have parts in the model that aren't held down enough. So what do I mean by that? This is a static analysis, linear static stress. Any loads that we apply to our model need to be in balance with constraints that are preventing them from moving. In other words, we need to have forces and reaction forces in complete balance, equilibrium. So if I have a 12-pound force on a part with no constraint holding it down, I basically have movement. And movement is not allowed in linear static stress. It'll just fail. Now, I constrained it though, right? I put a fixed condition on the bottom of the CPU. Yes, but I failed to specify any contacts. Contacts are an important concept that get introduced once you start working with more than one part in FEA and specifically here in Nastran In-CAD. Contacts tell the parts how to interact with each other. Are they hitting? Are they sliding? Are they passing right through one another and not interacting at all? Well, without any contacts, that's exactly what's happening. The parts are not going to interact at all. My 12-pound force is on my plate, but the plate does not have any contact assigned to the copper base or the CPU, so it's just kind of falling in the negative Y direction infinitely, hence failure. So contacts are handled on this panel up here, the contacts panel. There are manual ways to build contacts, which we would get into more in class. I'm just going to hit the auto button, and what that's going to do is look for parts that are close enough together that a contact is appropriate, and it's going to build it for me. Now, I'll get more into this during this presentation, but for now, I'm just going to leave it as is and show you what it looks like. Hit run again. Okay, complete. That's what I want to see. Hit OK. Nastran is going to load up a contour for me, load up a plot for me. And why don't I just get it animating? So again, we're looking at stress, and we're looking at exaggerated deformation. And now that I have contacts specified in between the parts, they are interacting with each other. So I'm not getting any singularity errors, but how are they interacting with each other? Well, if I look closely at, say, this area here where my mounting plate is tucked in underneath my acrylic block, well, look how as the mounting plate is bending downward, it's pulling the block along with it. That's not really what's going to happen in real life. Really, the block is held against the copper plate underneath the mounting plate with screws. They're not glued together or anything like that. What this behavior is the default contact type called bonded. And bonded is just going to do exactly what you see here. The parts that are in contact, in bonded contact, are basically one part. They're still separate in that they can have different material assignments, but they're going to move as one part. As this thing pulls down, it's going to pull the CPU, the acrylic block with it. Now, it's not the most realistic way of setting up this model, but it sure is the easiest. It's going to be the quickest way to get some results going in an assembly, and it's going to produce the least amount of headaches. And you'll see what I mean in a moment when I start playing around with different contact types. So it's not unusual that, number one, you start this way. Just get something going with bonded contacts and make sure that your loading looks good and that your material properties are working well, and that you kind of get a feel for what's going to move where and what kind of stresses you're seeing before you try and get too fancy by adding realism in here. And it's not uncommon either, if it's a larger assembly, to leave a lot of the parts in this condition and only put in the realistic contact behavior in the areas that are critical for you, the areas that you want to see the most realistic results. That's not necessarily the whole model. Let me stop that animation. If you look up here, back in my model tree, when we hit automatic, it created a new node up here for surface contacts, and it created pairs where it detected parts were close enough together. You have control over what that distance is, and we'd talk about that in a full class. Here are the three contacts that it created for me. You see the names of the parts are in the node, so it's the water block base, the copper base, versus the CPU, the mounting plate versus the acrylic top, and the CPU versus the mounting plate. If I click on them, you can see them light up in blue on screen, the faces that are involved in that contact. So there's the one that's attaching my mounting plate to the acrylic block. So these guys can be edited. Okay, this form here is the same one you'd get if you were creating a manual contact. And again, we would in a full class, but we don't have much time for that here. But we could see what it basically did. It picked the faces that are involved in the contact, and it selected a contact type, and you can see the type there is bonded. This little drop down here shows me the other options I have though. The opposite end of the spectrum in terms of realism and complexity from bonded is separation. Separation is the most realistic contact type we have. That's going to allow parts to push against one another and not penetrate. It's going to allow them to pull away from each other. It's going to allow them to slide against one another and apply a coefficient of friction if you so desire. It is the most realistic and the most costly to run. It's going to increase the run times noticeably, and it's going to create some headaches in terms of keeping parts constrained. I'll show you that in a second. There are some compromises in between bonded and separation. So if your real world condition might allow full sliding and separation, but one or the other is negligible, say you're only really concerned with the sliding and you don't want to see the minor separation that might occur, you would select this one here, sliding, no separation, and it'll do just that. It'll allow the sliding, but it'll keep the parts locked together. It's less costly to run, less of a pain in terms of degrees of freedom on the parts. And this one here is the opposite, right? Allowing separation, but not the sliding. Offset bonded will allow me to bond parts that are separated by a gap, which is actually unusual in these FEA products, and it works well in Nastran In-CAD. I like it because in the real world assemblies you're going to be working with, often parts are separated by small gaps because we need them that way for manufacturing purposes. In a lot of other products, you'd have to clean that stuff up, close the gaps, bring the parts closer to one another. Not the case here. If you're just going to bond them together, all you got to do is tell it, usually manually, that they're going to be bonded across that gap. If it detected this contact pair and you don't want it, you would just disable it. I'm going to switch this one, which is the it's the CPU versus the copper base, right? I'm going to switch this one not to full separation, but sliding, no separation. So where the CPU and the block come into contact, the copper is going to be pushing against the CPU. I don't expect separation there, but I might want to allow it to slide a little bit as they push against one another. So I'll use that one in this case. You can see the symbol changed up there. Here's my mounting plate versus the acrylic top. That's the one where, as the plate was bending down, I expected to see some separation there, right? As the block and as the plate pulled away from the block. So that's where I'm going to actually use the full separation. And then I'll go down here again with the sliding, no separation. I could do full separation on all three, but again, I'd be spending CPU time unnecessarily. I really don't expect to see separation there, so why bother having it check? Okay, so other than changing the contact type, I haven't done anything else here. Let's give it a run, see what we get. It's already taking a little bit longer, and I get another failure. Don't worry, this one was intentional. So what's happening here, I'm getting that same matrix singular error where it's telling me something's unconstrained. So what happened, it worked before because I was fixed on the CPU and all the parts were bonded together, remember, so they were basically one part. But now that I have something other than bonded in use, specifically my acrylic top versus my mounting plate is separation, well, the acrylic block is free to fall right off. It's free to float off into space. It's free to slide off in any direction. It's completely unconstrained, really. It would push against the mounting plate, but there's nothing keeping it from going in any other direction. And even though I technically don't have any forces that are trying to move it, that's usually not enough for FEA when you're working in a static stress problem. It wants to see it held down, even if there's nothing trying to move it. So in real life, these things are going to be bolted together, right? So ultimately, that's what I need to do to get this thing working here. So let's do that. I'm not going to put a 3D model of a bolt in there. I took it out for a reason. Those tend to be highly detailed little models of fasteners. And a screwed contact, a bolted connection, those are really pretty complex problems for FEA. Lots of little contacts in between those threads. lots of little details on the head itself. If you were really studying just that bolted connection, then yeah, you might want to go to that level of detail, but not with all this other stuff involved. You would focus just on that area. When it's just part of a system that you want to hold things together, you would use in Nastran In-CAD a connector. If you don't see that, by the way, I don't think they added that connector button to the ribbon until like 2018.1, maybe, one of the point updates for 2018. I don't even think it was there for 2018.0. So if it's not there for you, install an update and it might show up. Before that, you had to go down to the model section of your model tree here and find the connector node and right click and say you wanted a new one. But they've now put it on the ribbon, which is convenient. So what is a connector? I'm going to use several different types, so I'm not going to go into too much depth right now explaining them all. Let's just go right down to the bolt. The bolt offers me a couple different types. I can simulate a connection that goes through clearance holes and has a nut on the other side, or I can simulate one that screws into a bottomed hole, and that's what we've got in this case, and that's called the cap screw. So next it wants me to select the bearing surface or edge for my bolt head. So where is the under the shoulder of the bolt head going to be making contact with this assembly? And that's why I created these little circular faces here. Again, those weren't there for the design model, strictly here for Nastran for this purpose. Technically, I didn't need to do it. It will allow you to select the edge of the hole, but you're really focusing all the stresses of the bolted connection itself on a very small area that way, and it tends to work better if you can spread it out on a face. So that's what I've done. Pick that face, and then it wants to know the surfaces for the threaded region. Where are the female screw threads? They're in this hole here, which I could get by looking down the hole itself, or by using Inventor's select other functionality here. Select the inside of the hole, and once that kind of minimal information has been plugged in, you'll start to get this. It looks like a solid model of a bolt, but it's just a rudimentary glyph. It's not actually building a solid. What it's going to build is a structure that's essentially a line element going through the hole, and it's going to use the beam element type, which is a very simple way of representing structures that are long and have uniform cross sections. Much more efficient than trying to mesh a bolt in 3D, but will still give us useful information like the axial force that the fastener is undergoing as a result of the loads on the assembly. It's detected the bolt diameter from the hole I selected, but I can override that. So like a 540 is actually 1/8, so I might want to plug that in. I could plug in a washer if I wanted to, and that would extend the length of the bolt on the inside, right? Because it offsets for the height of the washer. These are countersunk, so I'm not going to put a washer height in there. And the useful length is how much thread is actually engaged. How long is the actual screw that is going into that hole? If it's not bottoming out, how deep is it going? So I'm going to say 3/8. What's the material that the bolt is made of? Select stainless steel there. And I can put a preload on there to show that it's already under axial strain because of the torquing during assembly. So 4.5 pounds there. Now, I can hit OK, and what that's going to do is create that part. Really, it's not a part. It's actually a mesh of a beam that represents a bolt. But I have 3 more to go. So I don't have like a pattern command or anything like that that's going to do the rest of them for me. But what I should have done while I was in this dialog is not hit OK, but come over here and hit this Create Duplicate button. And that would lock in the one that I'm just creating, but also start the next one, keeping the settings in the dialog box so I don't have to keep plugging in the diameter, the useful length, all that stuff. That's going to be retained. All I need to do now is tell it where that next one is going to be located. So I'd pick my head surface. I'll clear out the selection from the old hole and pick a new one. Okay, so that one's done. Hit the duplicate button, go to the next hole. you get the idea. That was my last one, so I'll go ahead and hit OK. 4 bolts now holding this assembly together. I'm going to give that a save, because who knows? Sure don't want to have to start this over. I don't have time for that. And let's give it a run. See if I got it. Taking a little longer, you notice. I've got more advanced contacts in there now. Those bolted connections have added some elements. The complexity's building, the runtimes are building, but it shouldn't take too long. Technically, once you've added surface contact into a problem, there is some nonlinear iteration that is occurring in the solution. I'd explain that more in a full class. So it does add time. Solution complete. Should load up that contour automatically. That's a setting, by the way, if you don't want it to do that for you. And now let's animate it and see what we've got. Zoom in on that area we were looking at before. Now you can see the behavior is a bit more realistic. That's what I expect to see. And that's going to change the stress profile, not necessarily in the plate so much, though maybe a little bit, because earlier the plate was fighting the block and the block fighting the plate, so there was stress in that area that wouldn't be there in real life. See down at the bottom, they're not separating, but you can see them sliding a little bit. With a bonded contact, that wouldn't have been allowed, and they would have been fighting each other. Again, stress as they fight against one another unrealistically. So I've added some realism into the model, but you could see how my initial failure, because of adding the surface contact, that's the kind of trouble that surface contacts are going to cause you. You now have to worry about constraining the parts that aren't bonded to others. And that's also why I say build simple and add complexity as you go. If I'd have built this entire model as complex as I want to get it, and then hit go and have it fail, well, now I have to sort through all kinds of stuff to figure out where my failure was. By running it again, as soon as I switched those contacts, I knew what the problem was, because it was the last bit of complexity that I added. I knew right where to go and who was causing trouble. Because I am going to add some more stuff to this. I want to throw some springs in here and some other connector types. I want to run a thermal. I want to add the thermal to this problem. So I'm just going to build that up and not try and add all that stuff, hit go, and watch it melt. I want to know that if it fails, why it failed. It's just easier to go about it that way. So next, these areas here where I've just kind of put a force, I do want to put some stuff on here that won't necessarily change the result so much, but more to show you what it looks like to build these kinds of structures. But maybe if I was interested in how much my spring was going to displace under that 12-pound load, I'd want to include it here, but not a 3D model of the spring, right? So I would use instead another example of a connector, and it's the spring type. And let's just show you what that's going to look like. I'm going to build a spring between these two work points that I've put into the model just for this purpose, right? I might have gotten to this point and realized I kind of want the spring there, but I got nothing to pick. Then I would close the Nastran In-CAD environment, go back to the model, plug in my work points, come back here and get back to work now that I have something to pick. So my start and end points basically for the spring is what I needed there. and I'm going to put in the stiffness of the spring. So 143 pounds per inch in the Y. That's what that K2 field means. We could go into more depth with this stuff in a longer class. You see, it just creates a little graphic of a spring, but it's really just going to be a single element that has a stiffness applied to it between these two nodes. And that's all it's going to do. Now I'm creating 4 of these as well, right? So I'm not going to hit OK. I'm going to hit create duplicate to lock this one in and go right to my next one. All it's really rating for is the start and end of each of these new springs. Create duplicate. You probably can't see that work point very well right there. I can barely see it. But that's what it is, just a point in space I've given myself strictly for these purposes. Okay, should be 4. Yeah, that's all 4. So I can hit OK on this last one. Now I'm not done. That spring is really just kind of hanging there in space right now. It's not connected to the plate. Another example of a connector called rigid or rigid body. Rigid body asks me to pick a series of or a single dependent entity. In this case, it's going to be this face, and then an independent point. Let me adjust the graphic there so you can see it a little bit better. So the face is the dependent point, which means it's dependent on the independent point at the bottom of my spring. So what's going to happen is anything that happens to that independent point happens to the entire structure that it's connected to. Any movement, any rotation, anything at all. These little red lines are actually elements, but they're rigid elements. They don't deflect, they don't stretch, they don't move. So it's really like a hard connection from one point to the several points where my spring is going to be in real life. So that attaches my spring to that pad. And I'm going to do 4 of those. Dependent entity, independent point, duplicate. Dependent entity and the independent point. That looks good. How many more I got to go? Just 1. Duplicate. There we go. Hit OK. All 4 are attached. Still not really done. If you think about what I've built here as it would relate to like a physical reality, I've got a spring attached to my plate, but I've got a spring that's basically attached to nothing. It's just kind of free floating there. It's not attached to my pretend thumb screw, which no longer exists. And there's nothing. This spring normally is wrapped around, it's coiled around the thumb screw, which kind of keeps it positioned in an axial Y direction manner, right? And there's nothing here anymore to actually do that. So this spring could technically go off in any direction and cause me all kinds of singularity problems. So I need to constrain it. But I don't want to constrain it so much that it's no longer allowed to move. Ultimately, I'm going to be putting my force on top of the spring. I want the spring to be able to deflect in this direction. I just don't want the top to be able to move in any other direction. I don't want to see any rotation, right? I want to stop all that, but still leave the axial flexure free. So I'm still going to use the constraint, but where I have just been leaving all these default settings in here to what are basically set to fixed conditions, I'm going to now play around with these 6 checkboxes here, which correspond to the degrees of freedom of whatever I've selected in the 6 degrees of freedom in 3D space. So basically, if I pick the top of this spring and uncheck TY, I'm basically saying that the top of the spring is not allowed to move in the TX because it's checked, so translation in the X is fixed. TZ is still checked, so translation in the Z is fixed. And all of the rotations at this point, rotation around the X, rotation around the Y, you get it, are all fixed at this point. The only one that's unchecked and the only direction that it's free to move is translation in the Y. So I've kind of given it a guide. I've restrained all other motion except the motion that I want, that I expect from the force. And I want that on top of all 4 of my springs. And I actually want to do on at least one of these springs, I'm going to do the same thing at the bottom. And I'll try and explain a little bit more about why once we get some results and get it animating. So I'll call this something logical here, spring constraint. Very creative, right? So some little glyphs there to indicate I've got constraints. Those look good. Everything looks good. So I've built in quite a bit of complexity here. I kind of had to go further than I'd really like to, but none of that stuff would have worked until all of those things were in place. So I'm kind of at the next step now where I can try and run it and see if I like what I got. But I do need to put these forces on the top of the spring. I didn't do that yet. So I'm going to edit the force I already created and put on the pads, but I'm going to move them from the pads to the top of the springs. So I will clear out the selections I had in there for those pads and now pick the top of each of these springs. So each one of them will get that 12-pound force pushing down on them. Okay. Give it a save. I usually do before I run. If it is going to dump you out, it's probably at that point. So save your work just as frequently as you've gotten used to saving it in Inventor work. So we're looking at 2 o'clock, not too bad. I'd like to be moving on to the thermal shortly, and it looks like we'll be able to. So we're not going to see much difference here in the results. We'll see the springs deflecting, hopefully, if I set it up right. But ultimately, the same force is going to be pushed up against those plates. It's just another way to set it up. A little bit more realistic in that I can see how much my springs might deflect. And I could play around with the stiffness of those springs if I needed to. Okay, solution complete. That's a good sign. Okay. So if you've been paying attention, on that initial part that we ran, the single plate, we were up around 20,000 PSI, right? And we're already down to around 16,000 PSI. So it has changed, and all that we've really been doing is adding more parts in to this point. I haven't been playing with the mesh. I haven't really changed the forces involved. But the sheer fact that, for instance, that face that I had fully constrained on the plate is no longer fully constrained. It's allowed to move down a little bit and flex because it's sitting on something that is actually elastic. So the copper base is moving as well. So instead of a rigid stop there, it has some give, and as a result, the stresses in those local areas are actually a little bit lower. So it does matter. As you're adding more parts, adding more realism in, it is changing the results. Notice how my stresses are not quite as uniform as they used to be. On 3 of them, I've got a kind of reddish spot there that's around my 16,000, 15,000 area. But the spot where I gave that extra constraint is lower. Let me get that animating. So I've kind of sacrificed realistic results, accurate results, quote unquote, in this area, in the name of stabilizing the model a little bit. If I hadn't held down the bottom of that spring in the other directions, think about what I had. I had all the tops of the springs stabilized so that, for instance, they couldn't rotate. And when I say rotate, I mean kind of the whole structure spinning like this, right? And those springs would just be kind of stretching and allowing that rotation. Well, in order to stop that, I really just took one point here and said, you're not allowed to rotate either. And that kind of gives it a little more stability here to prevent that tendency to rotate. Again, even if my forces aren't actually trying to do that, the fact that it's free to makes the model statically unstable. And Nastran In-CAD is pretty tolerant to that stuff and will detect slightly unconstrained structures and automatically constrain them for you in a very small way. So it probably would have ran, but I'm still just in the habit, and I encourage you to be just being aware of the stability of your model, because it might cause failures and you might get singularity errors. As a result of that, though, this particular tab is not free to move as much as the others anymore. So the behavior is different, the stresses are different. I just need to be aware of that and accept that these guys are probably representative of what all 4 tabs are going to see, and this one not so much anymore. Okay, before I spend too much more time on the structural, I'm going to jump into another analysis here where I want to bring in the thermal effects into this structural problem. So this thing's going to be heating up, right? It's going to be on a 100-watt CPU, and some of the areas on this model are going to be heating up quite a bit, and then fighting that is going to be the cool fluid coming into the acrylic block and removing the heat. So I'm going to have a pretty steep thermal gradient, and the parts that are made of different materials are going to expand and contract at different rates due to their individual thermal coefficients of expansion and their individual temperatures. So as they expand and contract, they're going to start to fight one another, especially the ones that are bolted together and they're made of different materials. You might see them fighting against one another at that bolted connection, parts getting squeezed, parts getting pushed away. That's thermal stress is what we're looking at here. So I could just add temperatures to this structural model without running a thermal analysis, but I wouldn't get a nice natural gradient. I'd be limited to applying uniform temperatures to faces, uniform temperatures to entire parts. It might be good enough to get a good quick idea, but if I jump over and do a thermal analysis, I'll get a real true gradient between the hot spots and the cool spots, much more naturally developed one, and a more accurate picture of the thermal gradient this thing's going to see in real life. And then I'll bring it in here. I'll transfer those results into this structural analysis as a load. So let's see what that looks like. I'm going to create a new analysis, and I'm going to change the analysis type from linear static stress to linear steady state heat transfer. See, there's a pretty big list of analysis types you have available to you. We cover quite a few of them. We touch on them at the very least in a full class, and we run a few others in depth. But if any one of these is specific to your needs, we can absolutely create more customized classes and mentoring sessions built around those applications. But no time for that here today. Linear steady state heat transfer. Heat transfer tends to be easier, in my opinion, than the structural stuff. We no longer have to worry about the singular matrix errors where parts are moving and flying off into space unconstrained, and static equilibrium and all that stuff, because there is no displacements in steady state heat transfer. We're really just going to be putting heat into the system and taking heat out of the system and looking at what temperatures develop as a result of that. So it tends to be a little bit simpler. So the idealizations are going to be the same. It hasn't done that stuff automatically for me because it's not the first time I've launched this assembly. I'm creating a new one after I've already created one. I only get that effect the first time I launch, but I do still have the idealizations that got created. If we look at kind of the structure of my my model tree here, this whole portion here is, you can see analysis 1, the first one I created, kind of grayed out and zipped up there. And here's analysis 2. So all these nodes here correspond to that one analysis. There's this whole other section of the model tree that's currently collapsed. And if I expand it, you see all this stuff here. These are kind of like storage bins that, as I'm adding loads and connectors and idealizations to an analysis, I'm not only adding it to that analysis, but I'm putting it in these storage bins at the same time for later use if I want. And I do, in this case, want to reuse some of this stuff. I don't want to reuse any constraints or loads because those are structural, but stuff like my idealizations, the solid assignments with the materials already in them, I don't want to have to do that a second time, and I don't have to. I can just drag and drop them up to my new analysis. So there's my copper. Here's my stainless steel for the mounting plate. I could have given these better names so I'd know what I was looking at. There's one for the CPU too, but I'm not actually going to use the CPU in this model. I'll show you what I'm going to do. I'm going to suppress that. So I'll just drag the third one up, which is my acrylic. Is there anything else I want to use? Not today, no. Okay, so I've got the idealizations done and the materials assigned. What I want to do is go to this portion of my model tree where I can see the assembly itself and expand it and see the individual components. And what I can do is right click on these components and either make them invisible, maybe just to get them out of the way, or actually completely exclude them from the analysis. Now the system won't be expecting a mesh, it won't be expecting an idealization assigned there, it'll just ignore it. I can still see it in kind of this semi-transparent way, but it's not a factor in this model anymore. Because I'm not pushing against it, right? That's the structural piece. And I could leave the CPU in there and have it generate heat for me. There is a load that's called heat generation where I can apply it to a volume and have that volume uniformly generate heat, and that heat will come out of all the surfaces on it uniformly. So it'd be kind of like an electronic component generating heat. I could have done it that way, but I chose not to in this case. I'm actually going to just suppress it and then apply a load to the face. That is the amount of heat that the CPU is pumping into my copper block. So if I go back to my PowerPoint and look at the problem set up there, 100 watts, right? So what I did was figure out the area of the face where the CPU is going to be in contact, and I split it out so that it's a separate region that I can now apply a discrete load to. I figured out what the size of that area is because the units we have to plug it in are per unit area. I can't just say put 100 watts on that face. I have to know how many watts per square inch or per whatever. So I figured that out already. It's going to end up being 0.0042 BTUs per second inch square on that face. That's my load. That's going to be basically my heat inlet. So I'm going to go to loads. Switch that force drop down to heat flux. Pick that face and plug in 0.0042. There's the units for me, BTUs per second inch squared, and I'll call this my 100 watt heat flux. I'm working in English units, right? Because I'm using an English CAD document. And the units that you're plugging in values in, and the units that the results are reported back in, are all driven by Inventor's current unit system. But the value I happen to know for that CPU is in watts, so I had to convert that ahead of time, or I could temporarily switch my unit system, come in here, plug in 100, and then switch back. But that was a little more laborious than just figuring it out. So there, my heat is going into the system. I could run it right now, but what I'd basically get is an infinitely hot problem. The heat is not allowed to go anywhere by default. So we're going to be removing heat from this system with a convection load on surfaces that are the surfaces that would be in contact with a moving fluid, whether that moving fluid is the surrounding air inside the CPU case or the internal flowing coolant water. In either case, we're going to represent that extraction of heat with the convection load. So the values that I came up with for that are over here. The internal, where the fluid is going to be going through, any surfaces that touch that flowing water are going to get 1.7 e to the minus 4 for a coefficient, and the temperature of the water is going to be assumed to be 72 degrees coming from the radiator. On the external, I came up with 1.7 e to the minus 6. That coefficient is an estimate based on the conditions you expect, right? How fast is the fluid moving? What is the fluid? Stuff like that contribute to what the coefficient is. It's just an approximation, but really everything we're doing here is just a fancy approximation. CFD could do a better job if you have that product, but if you're not designing things frequently that have moving fluids, you might not invest in that technology. And in that case, you're going to be using a coefficient to replace it. So let's take a look at what that looks like. Give it a save. I'm going to go to loads, Looking good for time, looking good. Switch to convection again, it's the same load. My coefficient, I'll do the external first, so that was 1.7 E minus 6 to 70-degree air. I'll call it external air. And then start picking surfaces that I know are going to be touching the air. This part can get a little picky and a little tedious, and you'll see that in areas where I have a lot of things to pick, I'll show you kind of some techniques and workarounds to speed that up a little bit. It's not too bad on like the acrylic block here. There's not that many faces to work with. So this is the external air touching the outside of the acrylic block, the top of the block. The copper base isn't too bad either. It's really only touching the outside edges of that base and the bottom, that, you know, where it isn't touching the CPU. And I should get those little faces. I guess I could say maybe that's the countersink under the screw and not pick them, but I'll pick them. Now the tricky one is kind of the mounting plate. There's a lot more faces to pick there just because there's curved surfaces that get broken out into their own faces. I've broken out more faces for those loads. It's going to be a bit more tedious. So I'll show you what I would do in a case like this. I'm going to hit OK to lock in what I've picked so far. And then I'll make invisible my copper block and my acrylic block, just toggling the visibility in the assembly model tree there. Then I'll bring back the load that I've already started, external air. I'm just going to double click on that to edit it. And what I'm going to do is window select everything on this mounting plate and then deselect by holding Control the faces that I don't want. It just turns out to be fewer picks that way. So what I'll do before I window select, what I need to do is filter my selection. And this is kind of handy in other cases as well. If you right click in these boxes that are waiting for you to pick stuff to apply loads to, for example, you can filter what kind of entities you're picking. By default, I'm picking faces, edges, and vertices all the time. And if I'm trying to go for a vertex, it might keep trying to offer me the nearby edge or the face, and it can be kind of a pain. You can come in here and filter it and say, I just want to pick vertices, and it'll ignore the others. And I want to make sure to do that here, otherwise I'm going to be trying to apply a convection load to all the edges, all the vertices at each, you know, meeting point for an edge. I don't even think it works. I think it throws an error, but surely it's going to add overhead to creating the load. So I'm going to filter it to just select faces and then do myself a window select to grab everything. And then hold Control and deselect the ones I know aren't touching external air. It's far fewer than the ones that are. So I'm just kind of working backwards. Kind of hard to see, but the color is changing when I deselect. It's just because there's blue in the way as well and blue adjacent to it that it kind of gets hard to see that you are in fact deselecting it. I'll deselect the insides of the holes, for example. The faces that are touching the base and the acrylic block and the inside. Everything else is going to be touching the air. I want to leave those selected. And now I'll hit OK to update that load. The more faces you have selected, the longer it's going to take to even apply the load. You'll see the dialog box stays open a little bit longer when I hit OK. And if I had not filtered my selection and picked all the edges and vertexes too, it would have taken even longer. These funny little symbols are how they represent convection loads. I think they kind of look stupid. They don't really help me. So I go to the load in the model tree there, right click on it, and just toggle the display, and it hides the glyphs for that particular load. Not necessary, just a picky thing. Save my work. Now, the internal convection is the same problem, right? Look at all those little faces I have in there on those fins. I don't want to be picking those individually. I want to do a window select, and I'm going to do the same thing. I'm going to start a load. I'll pick the easy stuff first. Okay, this is going to be convection. It's going to be 1.7 E minus 4, so a higher rate of heat removal due to the cold water. I'll call this internal water. and start picking stuff. The insides of the inlet and outlet, basically, for the acrylic block. The walls inside that pocket inside the acrylic block, that's where the fluid is actually flowing around. This stuff's relatively easy using Select Other. And the top of the pocket too, don't forget that. Okay, so that's like the inside of the acrylic block. I'll hit OK to lock that in. I know none of the coolant's touching the mounting plate because there's actually a little gasket in there. So I know I can hide now the acrylic top and the mounting plate. Get right down to my copper block. Again, edit the load that I've already started, internal water. Filter my selection for faces. Window select. Hold Control. Deselect anything that's not on that inside pocket. The insides of my holes, for example. The faces on the outside. The bottom. And those little pads for my screws. Once I get those deselected, the rest I want to keep. So it's probably a couple hundred on those fins. That would have been real tedious to pick them that way. Better to window select and deselect. Now when you see me hit OK here, you'll notice, again, a little bit longer than even the last one because there's just more faces to apply. I've hit OK. I'm waiting for it to apply. I'll know it's done when the dialog goes away. And then we should be just about ready to run it. Now we're looking here, 220, and not bad. Almost there. I can see the symbol starting to pop up. I really only see this in this kind of load, just because the nature of it, there tends to be a lot of faces that you select. There we go. I'll hide that one too because it's kind of ugly. I'll bring back the visibility of my other parts and give it a save. Now contacts is still a part of this equation. We're not doing like separation and sliding or anything like that because nothing's moving, but we do still need at least a bonded interface between the parts. Otherwise you won't see any heat transfer. You'll know you forgot because if I ran this now just like that, I'd probably see that the copper block was really hot and the other two were at the 70 degrees or the 72, depending on the contacting fluid, and there'd be no gradient at the interface. And you'd see it, and oh, I forgot to run auto contacts. Yep. So I'll run the auto. It'll build the bonded contacts for me. Now we haven't played around with the mesh settings yet. We've really just been hitting run and letting the system run its default mesh. And the default mesh, what it's really doing, it's looking at the CAD geometry, and it's looking at the idealization for the kind of element we told it we want to use, and it's saying, okay, I need to rebuild this shape that you fed me out of those building blocks. So it's going to take a look at the geometry and rebuild it out of those little tetrahedral elements, and that's what you call the mesh. It determines an appropriate size for those individual elements based on the CAD geometry, or at least it's usually appropriate. It tends to do a pretty good job of that default mesh successfully meshing and successfully running. But it's by no means the last that you'll see of that mesh. You really should, and the default mesh it tends to be coarse. It does affect the results, and they can be improved by refining the mesh, and you're going to want to. Not necessarily right away. You might just want to get it running like I have here today. Set it up. Leave the default mesh in there so that it's running fast and giving me feedback quickly. I get a general sense of the stress and make sure that this design candidate is even worth spending time on. If I see right away that my stresses are, up over, well over yield, then maybe I don't bother spending too much time refining this model, but go back to the drawing board and edit the geometry a bit. So that's what the default mesh is intended for, to get you some results quick. Once you do have a model that you want to pursue, a design that you want to pursue, and get a more accurate picture of how it's going to behave in real life, you're going to want to refine the mesh. Actually, I think I have a little spiel about that in here. Yes, I do. Do that real quick. So on the left-hand side here, you'll see a CAD model. On the right-hand side, a mesh generated using that CAD model based on the tetrahedral element. So you can see it's made up of those little chunks. And you can see that the shape isn't quite right? If you look at the big hole, for example, it's more of a hexagon than round. And that's really because the mesh elements are too large. The pieces that I've given it to work with are too large to adequately capture the curvature in that geometry. And the further you deviate from the actual real-world shape that you've designed in the CAD, the further it's going to tend to deviate from real-world behavior. You're actually simulating a part that has a hexagonal hole there. It's not behaving like it's round. Don't worry, we're not going to do any math here. This is just an analogy. Let's say I wanted to find the area under this curve. I know the function, which is handy because now I can just use some basic calculus, integrate that function, and get pretty much the exact answer. But what if you don't have the function? And we don't have a function for our part, right? We don't have a function for this assembly that says how much it's going to displace when I put a force on it. So when you don't have a function, when you don't have something that you can get an answer from, you approximate. You would do it here for this graph if you didn't have a function, and you're going to do it in your CAD model as well. And you're going to do it by rebuilding that shape using other shapes that you do have functions for. Right? I know what the area of a rectangle is, so I can rebuild my curve out of some rectangles, add up the area of those rectangles, and have an approximation of the area under the curve. So it's an approximation. It's a pretty good approximation, but it could be better, and it could be better if I make those elements smaller. So now you can see that my approximation better adheres to the curvature. It's a better representation of that curve, but I've doubled my work. I now have to solve twice as many problems. So it's going to take me longer. And that's a trade-off. It's always a trade-off between this accuracy, if you can call it that. We'd get into that discussion in class too. What does it really mean to be accurate in an FEA model? And the time it takes to run. Right? So in this case here, I doubled my work and I only gained 0.5 percentage of error, 0.5 percentage point. So not really worth it in that case. And there comes a point in your mesh as well where it's not really worth it. But initially, you're definitely going to want to reduce that element size at least once. I'll get to that. Do I have? No, I guess I don't have that. So that's the meshing in a nutshell. We'd get into some of the techniques for understanding how far you have to go before you can trust the mesh you have. When are you done refining, right? But for now, how do we just edit that mesh at all? Look up at that mesh panel. You got this big old button that says mesh settings. This has changed in 2018 as well, I think even after a point release. So if yours looks a little different than mine, you're probably just an update or two behind me. But the functionality is the same. The real box that matters here is the element size. They've given you a slider now that adjusts that size, but you can always just type in a value, and I'd say you typically will. So in this case, I know that I'm going to go with a 0.05 inch element size, and what this is editing is the global mesh. Every part is going to get the same size element, and then we're going to look at how maybe we could vary that by part and how we can locally refine a mesh when we get back to the structural. But this is kind of the quick and easy way to refine everything globally. Okay, so that is the 0.05 mesh. If you were paying attention to the way the other one looked, the pieces were a lot bigger than this. We talk about it in the full class, kind of the different considerations that come up with a thermal problem versus a structural problem. In a thermal problem like this, I want a nice uniform mesh. I can get away with a pretty fine mesh. It's going to run faster than a structural problem would, so I can afford to. This is still probably a little bit coarse. I'd probably end up going finer. But just for the sake of getting something going, I'll leave it as is. So we've got everything we need, I think. Idealizations, materials. We've got an inlet for the heat. We got outlets for the heat. We've got a mesh. Let's see if I got it. It is going to take longer to run, you'll notice, simply because I've refined the mesh a lot more than that structural one was. But in general, steady state heat transfer is going to run faster than structural problems when the meshes are the same. If possible, and you plan on transferring these thermal results to a structural, it's good to have a finer mesh on your heat transfer problem than on the one that you're transferring it to. It just tends to work better that way. The meshes are going to be different, most likely, because like I said, there's different considerations in those two types of problems. But if your thermal problem is a better mesh, a finer mesh than your structural, you should be in good shape. When you go the other way, you tend to see some weird behavior. Okay, it's done meshing. That step alone took a little bit longer, you'll notice. Try not to fill this awkward silence with incoherent babbling. Takes discipline. Okay, complete. I like the sound of that. I'm going to change my scale here real quick. Get that looking a little more realistic. I've got a outlier node there that's throwing off my scale, and I'd explain more about why. We do the same problem in a full class. I do like to bring in this problem and run a little bit more slowly, in a little more detail. For now, let's just change that scale. Yeah, it looks better. So this is typical of thermal results, right? The temperature is the output. We get a temperature at each node. And we can see the hotter zones more gradually transitioning into the cooler zones. This is what you can't get in structural alone without running thermal. So you can see kind of how mesh would come into play here. If you think about each one of these points where the elements meet up as a data point in the curve of this thermal gradient, the more points I have, the more natural the curve, the more smooth it's going to be. If I have too few points, then I basically have a jagged line that represents that gradient, and it's less accurate, it's less real life. So the more data points you give it, the better the result. Okay. That's all I need to see with that. What I've basically been doing there, oops, I didn't mean to finish the entire environment. Let's go back in. Meant to just finish that analysis. I was basically generating a load there for my structural analysis. I now have thermal results at each one of those nodes that I can now bring in as a thermal load on my structural problem. Let's do that. I just hit the big green checkbox at the top to leave the environment rather than switching to the analysis. And it's getting there. Tick tock. If you have one of those loads that takes a while to apply, it'll take a while to open the model as a result too. There we go. So I'm going to go back to analysis 1. I'll just right click on it there and activate it. So you can see this default mesh, how much coarser that is. Right, I do want to adjust that now, now that we're kind of nailing down this problem and getting more advanced with it. But first, let's bring in our thermal load. What I want to do here is I want to have a couple different subcases, is what they call them, down here in the model tree where the load actually exists. It's actually under subcase 1. We only have one subcase now, but a subcase is like a different combinations of loads and constraints that you can explore within the same analysis. If you want to change things like idealizations, and mesh from one run to the next, those are going to be separate analysis. If all you want to do is change the load magnitude, direction, location, you can just vary that with a subcase. You don't need to create a whole new analysis. So that's what I'm going to do here. I'm going to create a subcase that's just the structural and just the thermal, so I can kind of see their effects independently. So I'll create a new subcase here called like thermal only. It is going to need constraints, so I'll make sure those are included, but I'm not going to put the spring load on there, 12 pounds. The only load that I'm going to incorporate in that subcase will be the thermal, which I haven't brought in yet. So maybe I'll rename that original subcase it gave me to structural only. Structural engineering spelling. There we go. Okay, so now you see a thermal only. There's no loads in it yet, but I'm going to create one now. I'll go back up to my loads command. And this one I'm going to use here in this dropdown is all the way down at the bottom. It's called from output. This is the same one that you would use if you were going to bring in CFD results. It's going to ask me to browse for a file that contains my results. Down at the bottom of this dialog, you'll see I have a choice between an FNO file, which is a Nastran output result file, and a CFDST, which is a Autodesk CFD file. In this case, I want to go for an FNO, and I got to find my results. Oh, I was in the right spot, wasn't I? So these ones I've already created, renamed, and tucked away to a safe place so that I can go grab them easily. But what happens is they get generated and put into a subfolder that gets created right next to the CAD that you ran, and it gives it kind of a funny name. So if you were just going to go browse for it now without renaming it ahead of time, you'd probably be looking at like timestamps to see, okay, this is the latest one I ran, so that must be the thermal. Myself, I'll run it. I'll go find the files in Windows Explorer and just rename it and put it somewhere safe. None of this stuff actually needs to be saved, but these FNO files are the results. So if you want to save the results, you would keep those. You can give them another name like I've done here. So I'm browsing for thermalresults.fno. If I were browsing for a CFD, I could tell it whether I want the thermal or the pressure. And in this case, I only have thermal available because we don't get pressure from Nastran. So I'll call this my thermal load. Down here, notice how I have the names of my two subcases. So if I hit OK right now, it would be putting this load into my structural only subcase because it's lit up in blue there. I don't want that. I'm going to click on it to unselect it and then pick the thermal only. To hit OK, it'll go in there. I could always move it after the fact, but while you're creating it, you can put it in the proper subcase. And let's see, I think that, oh, there's one step I always forget to do. Let me show you. The material properties that come from Inventor and the libraries built into Nastran In-CAD don't contain a pretty critical property if you're working with thermal stress, and that's the reference temperature. So basically, these things are going to grow and contract now based on the heat that I'm putting on them. How much it's going to grow is based on thermal coefficient of expansion and its reference temperature, and basically the difference between the reference temperature and my applied temperature. The bigger the difference, the bigger the percentage of growth or contraction. So my stress-free reference temperature really is what the TREF is. Kind of think of that as like, what temperature was the machine shop when they machined my mounting plate? You know, so any hotter from there, any colder from there, and the shape is going to change. Well, right now there's nothing in that TREF field, so it's basically assuming 0, and I think it assumes 0 Kelvin, so we're talking like absolute 0. It's a pretty big difference between the 70 or so degrees Fahrenheit and the 0 Kelvin. So what you end up with is massive displacements, usually singularity errors. Thing just explodes. So if you forget to put this in, that's what's going to happen. You'll get either an error or these huge unrealistic displacements. Then you'll know, oh, I probably forgot to put something in that TREF field. So I'm going to go ahead and do that for all my materials now. Acrylic's already done. Oh. Yeah. Stainless. Again, these are the ones that it pulled out for me when it created those idealizations at the beginning. We'd look at how to change them, how to create our own materials. We'd go into more depth in this in a full class. Now, I just want to run the subcase of thermal. I want to ignore the structural for now, so I'm actually going to kind of suppress that structural only subcase, deactivate it, really. You right click on it, you uncheck activate. Otherwise it would run them both, and I'd be running it twice, and I'm not really interested in seeing the structural yet. Actually, we've already seen it, really. So I want to see just the effects of the thermal and show you what's going to happen. Let's see how I did. Give it a save. How are we looking for time? Getting there. And I'm going to run it. I kind of just want to show you the thermal effects alone, in case you've never run a thermal stress and have no idea what I'm talking about. What you're going to see now is the parts growing as a result of the thermal expansion. And you'll see that they, assuming I set it up correctly, of course, you'll see that they are growing at different rates. They're made of different materials. They have different temperatures. And the result can be stress. And that stress can be a big deal. Doesn't turn out to be in this problem. It's not a huge effect. But it could have been. It's worth checking. Could have cracked my acrylic block because there was too much stress at the bolted connection. You know. Looking at quarter of, I would like to refine the mesh a bit more with a local, using the table, see if I can get that done for you. Show you what a geometry change looks like. Like I said, I just got a couple slides to wrap up. I'll probably do that at 3 o'clock regardless, and if I got to run a couple of minutes over to finish the model, I'll do that. Okay, that's done. See if it loads a contour for me. I think it will. Maybe not. I'll double click on displacement, get it going. Yeah. The displacements are pretty small overall, so the exaggeration tends to be kind of funny looking. But it does give you a picture for what's happening. Once you add it to the actual structural and the 12 pounds is involved, the scale of the deflection at the tabs is so much higher that the thermal expansion effects are much less visible, if at all. But this is just thermal alone, no 12 pounds on it, and you can see what we're looking at for potential thermal stress. Look how much more the acrylic block is growing compared to the mounting plate, right? And those two, or the acrylic block versus the copper, for example. And those two are bolted together, right? So we're creating stress at that bolted connection. How much? Doesn't turn out to be too much in this problem, but certainly could have been. That's thermal expansion. Let's stop that. What I'll do is I'll create a subcase that's everything now. It's the structural and the thermal. So I'll create a new subcase called all loads. And while I'm creating it, I can select which out of the loads and constraints I've already created, which ones do I want to include. I'll include the 12 pounds, I'll include the thermal, and both my constraints. These guys are all for the thermal analysis. I don't want to include those. So ultimately, that'll be my final run, is that all loads. I'm going to suppress the thermal only now. But before I run that last one, let's refine this mesh a little bit. Show you what kind of control you've got here. Ultimately, the mesh I settled on is this. And what you see up here is a table, a mesh table that I'm going to show you, which allows us to control the size of the mesh on a per part basis. In fact, every one of the mesh settings can be controlled on a per part basis, including the advanced settings. And then I'm going to put a very localized, even finer mesh on just one of the tabs, assuming that they're all going to be representative of each other. I don't need to refine them all. I'll just refine the one and see how that does with that final small mesh. So you can see what a local mesh control looks like as well. So let's see if I can remember these values here. My CPU, see how my mounting plate is what's important to me in this analysis. So I'm going to give it a good small 50 thousandths element. The CPU, not so much. I'm just pushing against it. I don't really care what's happening in the CPU. I'm not really all that concerned with the accuracy of stress and strain calculated in that part. So I'm going to go all the way up to 0.2 in that one. And then kind of a compromise between the two for the acrylic and the copper. I'll just go 0.1. And then finally my localized mesh control, I'll go all the way down to 25 thousandths for my element size. So the table is on the mesh panel here. You hit that table button. You can see a row for each part. The top row is actually the assembly, and that's the size that's getting used globally. So what I'll do is I'll plug in some new values for my other parts. Mounting plate's going to be the 50. Water block base is going to be 0.1 and 0.1. Let's hit OK. It's going to remesh when I ask it to by hitting Generate Mesh using those new settings. Mesh matching is not required, if you know what I mean when I say that, which gives you some flexibility as to the element size on a per part basis. They can be much more independent of each other in Nastran In-CAD. So that's the kind of global mesh I'm going with, and then over here I'm going to locally refine it with a mesh control. This button here, and I can control it on individual points, edges, or faces, or entire parts. I can do it that way too. I'm going to do faces here, so I'm going to select that faces box and start adding faces to that. I'll go with the inside slot there too. Okay, and on those faces that I've selected there, what size do I want? I plug that into this box. I'm going to go 0.025. I won't see anything when I hit OK. I got to regenerate the mesh again to incorporate those new changes. Okay, now so you see what happened there. On the faces, I get the new element size that I asked for, and it kind of transitions naturally using what's called a growth rate to the element that was assigned to the whole part. Right, there's that larger 0.05 that I assigned in the table, and it kind of transitions gradually down to the 0.025 I asked for on the wall. I can control basically how far this new small size penetrates into the other part by varying the growth rate. That's one of the advanced settings that you'll find. And I'd go to the mounting plate. We talk about some of these advanced settings, but this one, the growth rate, is basically saying that an element's neighbor can't be any larger than 50% larger, 1.5 times. If I want to make it a more gradual change and basically spread out the effect of these controls, I'll reduce that number. So now I'm basically saying an element's neighbor can't be larger than 10% larger than it. And again, won't see those changes until I regenerate. Now you see it's a bit more uniform in there. They're all kind of roughly that 0.025, maybe a little bigger as you get away from the walls, but that kind of spread out the effect of those mesh controls. Now I've got at least 3 elements, 4 in most places, across the thicknesses, which is what I'm looking for when I expect bending in a member. So I expect a nice looking result there. Don't want to run it just yet. We don't really have time. So what I'll do the run last. Let's say that we ran it and it came out great. We released it to market. Everybody's happy. But now, the manager comes back and says, we want to expand the compatibility of this particular mounting plate. So, different motherboards will have different positions for these standoffs. If we can extend the length of this slot, we can use it for another socket type, something like that, right? Without too much more work. So what's that going to look like? Show me. So we have a model set up in Nastran In-CAD already. We're already sitting in Inventor, so it's pretty easy to go take a look at that and see if it's going to work or not. What I would do is finish the Nastran In-CAD environment, and now I'm basically back to the standard modeling environment. The change, I've already incorporated it into the part, so I'm just going to unsuppress it basically. And that's at the mounting plate level. I'm going to edit the mounting plate. There's already a feature in there, an extrusion and a pattern for it. And you can see what it does when I activate it here. Sure, I'll check it out. Slot gets longer. Return to the assembly environment. Go back into the Nastran In-CAD environment. Might actually finish this on time. Let's see. I get some minor complaints. What happened here is the mesh controls that I applied, right? I changed some of the faces that they were applied to, right? I had some mesh controls on that internal slot. I now cut that thing longer. I probably changed the surface ID number in the CAD database. Who knows what changed, but it broke my mesh control is what happened. And that's realistic. Depending on how severe the change might be, there might be some finessing that needs to be done to restore this model to a running condition. Ideally, it's ready to go. Ideally, the change you've made is nowhere near any of your loads or constraints. You don't break anything, and you just hit go. It's ready to run. Actually, not quite yet. You could see my old mesh kind of overlaid on the new CAD geometry. All I need to do is regenerate my mesh to have it incorporate that change into the CAD geometry. Since it broke my mesh controls, I'm just going to edit that. I see a little exclamation point there telling me it needs some attention. So I'll just reapply it. The settings are still in there. I just need to pick the faces again. Like I said, sometimes things will adjust themselves just fine. Say maybe some of these faces were still intact. They'd still be in there, but it apparently just broke them all, and I need to repick them. Check those table settings again. Everything looks good, and regenerate. And now I'm ready for my final run. So I'm going to save. I'm going to hit go and do my closing slides here. And if you want to, stick around and see if I got an error message or results. I know, I honestly don't know either way. Surprise ending. Okay, so I'm going to hit run. Go back to my PowerPoint and wrap this up for those of you who need to get out of here. So, what to do next? Well, you sign up for the full class, of course, right? It is 20% off for a limited time, and it's going to look and feel a lot like this, but less rushed and more in-depth. We have public classes on the schedule right now, so you can go sign up on our website or just reply to that poor salesperson that's been bugging you about this and you've been ignoring. It would be good for their self-esteem to hear from you. So we also offer customized classes that would be delivered exclusively to your team, in which case the content of the course is flexible or even based on your models. That's a different cost, of course, so reach out to us, reach out to your sales rep if you're interested in something like that. And of course, keep us in mind for any of your simulation needs. Hagerman is uniquely qualified in this realm. Engineers like myself are on the phone all day long, helping customers or potential customers figure out how simulation can benefit them. So give us a call. We'll talk about what you actually do and how we can improve how you do it together. That may mean we provide you with software, or it may not. Maybe you already have the software you need, but you need some help adopting it. We provide standard and custom training on everything we've talked about today and more. We can deliver that training remotely or on site. Or maybe you don't have time for any of this right now and you just need some results. Hagerman & Company has a full engineering consulting services division that can deliver the data you need fast. So for those of you who need to get going, thank you for your time. For those of you who are interested in whether I've failed miserably or succeeded here, stick around for another couple minutes. guess maybe I can explain what I meant earlier about how you technically going nonlinear when you add a surface contact. If you think about what's going on with the separation contact, I keep calling it surface, but it's separation. If parts are separating, then the area that's in contact is changing, right? So really the force is getting transferred between the two, or the location of those forces is changing. And there's no way for the system to know in one pass how much it's moved and how that affected the loading. So what it basically does is kind of runs it once, sees if it detects any separation, runs it again with that separation in mind and the new location of the forces involved because of the new contact points, and checks to see how big of a difference there are between that first and second run. And then it'll do it a third time and check to see how much it's changed from the second to the third run. And it'll keep doing that until it's detected that it's not changing so much anymore, and then it figures, hey, I must have come up with the final balance between contact area and forces. So it's not something that can be solved in one shot. It has to iterate. So you'll see in the log iteration 11, right? It'll keep doing that until it reaches a certain criteria for the difference between the two runs. And that's just nonlinear iteration in general. When you get into nonlinear problems, that's going to be a part of the solution all the time. It always adds to runtime. It takes longer, adds complexity. But that's about as nonlinear as you're going to get in the linear static stress analysis type, if that made any sense. Should be getting there. Oh, looks like we're coming near the end. Is it complete? Did I pull it off? Let's check that von Mises plot. Didn't get an error, but did I get reasonable results? Looks like it. That's good. Look how much nicer the stress profile is through the cross section there with our finer mesh. We've got it, neutral stress at the neutral plane as we'd expect, and it still looks a little chunky. We could probably refine it a bit. But ultimately the answer to the boss is no, this is not going to work. Our stress is now exceeding the yield point. We've just taken too much material out of there, it seems. So whether or not that's a happy ending is up to you. We've avoided a costly mistake. I guess that's happy, rather than machining a bunch of these things and having them fail. And we did get successful results. So thanks for hanging in there, and thank you for your time. Back to you, Ashley.
Okay, thanks, Rob. This will conclude our broadcast. If you think of questions later, you can simply reply to the confirmation email or reminder email that you receive from GoToWebinar, and we can get those to Rob or whoever to answer your questions. The survey will pop up as we close down today, and we ask that you take a few moments to fill that out for us. And thanks, everyone, for attending. Have a great day.